When millions of pounds of downward force press on a structural beam, the visible bending is only one part of the structural response. Inside the material, a complex interaction of internal forces prevents the steel from failing under the load. To understand these internal mechanics, we must look past the macroscopic deflection and isolate a single microscopic cubic element located at the beam's neutral axis. This diagram isolates that cubic element to illustrate a state of internal imbalance. The vertical load applied to the beam creates a shearing effect, generating downward and upward forces on the opposing vertical faces of this microscopic cube. Because these forces are offset, they create a rotational moment. If this moment were not countered, the internal material would be unable to maintain its position, leading to the immediate breakdown of the beam's structural integrity. The structure maintains stability through the principle of complementary shear. The vertical forces are instantly accompanied by horizontal shear stresses of equal intensity along the top and bottom faces of the cube, neutralizing the rotation and establishing static equilibrium. This principle dictates that any vertical transverse load applied to a structure requires the existence of these horizontal sliding forces along the longitudinal layers of the material. To engineer a beam safely, we must calculate the exact magnitude of these internal sliding forces at every level from the top of the section to the bottom. The governing shear stress equation, tau equals F times AY bar over I times B, provides the mathematical framework. For any vertical cross-section, two variables are fixed: total vertical shear force, F, and total moment of inertia, I. The stress output depends on two dynamic variables. The first is B, the actual physical width of the section at the horizontal slice being analyzed. The second is the first moment of area, AY bar. This is the product of the area above the cut and the distance from that area centroid to the neutral axis of the entire section. At the top surface, there is no area above the cut, so AY bar starts at 0. As the analysis moves lower, accumulating more area, AY bar increases until it reaches its maximum value at the neutral axis. Since F and I are constants, the internal stress profile is determined by the cross-sectional geometry and how it manipulates the relationship between accumulated area and width. Applying this equation to a basic rectangular profile establishes the fundamental baseline for shear stress distribution. At the extreme top and bottom fibers, the first moment of area is 0, which means the shear stress at these edges is also 0. As the mathematical slice moves toward the center, the accumulated area grows while the width remains constant. This consistent relationship generates a parabolic stress curve across the depth of the beam. In rectangular sections, the maximum shear stress is located at the neutral axis, where it reaches exactly 1.5 times the average shear stress across the entire shape. A solid circular section introduces a variable width. Because the width increases as we approach the center, the parabolic curve becomes slightly flatter compared to the rectangle. Even with this changing width, symmetry ensures the maximum stress still occurs at the neutral axis, reaching a value of 4/3 of the average stress. For these uniform, symmetrical profiles, the peak transverse shear stress is consistently found at the geometric neutral axis. This alignment between peak stress and the neutral axis isn't a universal rule. It fails when the section's width changes significantly relative to its area. The isosceles triangle provides a clear example of this shift. As we move down from the apex, the first moment of area increases, but the width in the denominator also grows. These competing growth rates cause the maximum shear stress to occur at mid-depth, or h/2, rather than at the neutral axis located further down. The stress at the triangle's actual neutral axis is actually lower than the peak stress located above it. A square tilted on its diagonal exhibits the same behavior, with the maximum stress shifting to a depth of 3/8 from the top tip. The full matrix of solid shapes confirms that width is the primary factor in determining where the stress peaks. When the physical width of a shape increases faster than the accumulation of its area, the point of maximum shear stress is mathematically shifted away from the neutral axis. Structural engineering utilizes these geometric relationships to design built-up shapes that place material only where it is most effective. Analyzing a standard I-beam shows how width manipulation creates structural efficiency. The top flange is wide, and since width is in the denominator of our equation, the resulting shear stress in the flange is minimal. However, the calculation changes at the junction where the wide flange meets the narrow vertical web. Because the width drops suddenly, the shear stress increases instantly. The stress level multiplies by the ratio of the flange width to the web thickness. This ensures that while the flanges primarily handle bending, the thin web is responsible for resisting the vast majority of the transverse shear load. For unsymmetrical shapes, like T-sections, the distribution is more complex. Engineers must first calculate the position of the shifted centroid before they can map the 4 asymmetrical stress zones across the flange and web. Engineered efficiency is achieved by manipulating the width to concentrate specific forces within designated parts of the beam. Advanced structural profiles, such as thin-walled C-channels and angles, require a different analytical approach. In these sections, the wall thickness is so small that the shear stress is assumed to be uniform across the thickness of the material. Because the stress is uniform, it is expressed as shear flow, the shear stress multiplied by the wall thickness. This treats the force as a continuous stream along the profile's centerline. This shear flow travels the entire path of the flanges and web. This establishes an internal force path linking the entire cross-section into a single circuit of stress. Shear in thin-walled engineering is analyzed as a dynamic flow, and its path determines the structural behavior of the entire member. The internal shear flow in thin-walled open sections makes them highly susceptible to twisting. Loading the geometric center of a C-channel creates internal torque from shear flow, causing torsional rotation despite a purely vertical load. To prevent twisting, the load must pass through a specific coordinate called the shear center, which neutralizes the internal torque during deflection. Failure to account for this can result in sudden twisting instability and lateral buckling of the structural member. For sections like the C-channel, the shear center is a critical point of stabilization that often exists in empty space, entirely outside the physical material of the beam.